Now we talked about the electrostatics and then how these forces are going to work, and the bus actually when it comes to one charge. So the field, how to represent the field of that particular charge. And I gave you a homework. Draw the field pattern, electric field lines, or pattern of the electric field lines regarding two positive charges and two negative charges as well. So answer should be somewhere here we have a positive charge. Let's say we have a positive charge. Here we have a positive charge. Okay, let's say plus Q, and somewhere here. Okay, this dashed line represents the line segment. Okay, interconnecting line segment. That's all, and both are going to be positive charges. So let's say, let me just get that thing as plus capital Q. This thing also to be plus Q. How the field lines are going to go, and I'm going to, before that thing, I'm going to draw a reference line segment, which is going to be the perpendicular bisector that one is going to be the perpendicular bisector to that QQ line segment. Perpendicular bisector. Bisector means this portion towards left is equal to that portion towards right. Okay. I think you got it right. I mean, this length is equal to that length. At the same time, this angle is going to be 90. That's why this green line is called the perpendicular bisector. Because this field pattern is going to be symmetrical. Okay, right, fine that. So field lines are going to be how? If we just get this, right? One line segment, one line is going to be something like that. Yeah. So therefore, the corresponding line is going to be this. Okay. Probably another line is going to be something like that. Okay. And the corresponding line is going to be something like this. They will check just for the shape, right? And that line is going to be something like that. Okay. And the corresponding line here is going to be something like this. And the other line is going to be from here is going to be something like that probably. And another line is going to be something like this. Right. Like these two lines. And one line is going to be like that, and another line is going to be like this, and the other line is going to be probably like that, and the other sometimes like this. Okay, it's getting connected to that point, and one is going to be like this, and the other one is going to be like that, likewise. Okay, so there will be a point somewhere there here. So field line will be up to there, right? And again there will be a field line up to that point, but they don't get intersected. They are not going to meet that field line and this field line. I mean these two field lines, that field line and this field line. They are not going to, continue through that. Through the midpoint or this by crossing this green line, and they are not going to join with each other. That's the reason why. Let's come back to that point later, just after marking the arrowheads. If I place tiny testing positive charge, one important thing, positive charge here also positive is getting repelled away, 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 getting repelled away. If I place a testing positive charge here again, by this one, it's dominating, it's getting repelled. Why dominating? Because that one is a little closer to this one than this one. Actually both are going to repel, and here also is getting repelled, here also is getting repelled, here also is getting repelled, away, away, and away. Right, so here also is getting repelled this way. If you place a time testing positive charge here, this one is dominating, so that testing charge will be pushed away. Then So that part is going to be okay. The thing is regarding the point which is going to be exactly at the mid, somewhere there here. What is that point? If you place a testing positive charge there, that testing positive charge is equally distant, away. That testing positive charge is equal distance away from both the source charges, this plus Q as well as this plus Q. So meaning what? Both the source charges are going to, parent charges are going to exert the same push, same repulsive force on this testing positive charge. For example, let's say by this Q, by this Q on that testing positive charge along that way 10 Newton. By this Q also on that testing positive charge along that way 10 Newton. 10 and 10 getting cancelled. So therefore this testing positive charge has no net force to move, so that testing charge is going to stay at rest. This area. So therefore is something really important. If I just do that in a different color. Okay. At that point, let's say for example, if we get exactly that point, there is no force acting on the testing positive charge. So the important point is, now if I get the electric field intensity at that point, electric field intensity we defined, E is equal to the force F divided by the testing charge Q. Now what we said, the force acting on that testing positive charge, actually the net force acting on that testing positive charge is equal to 0. Why? Because both the source charges are exerting equal opposite forces on that. So therefore the net force experienced by that testing positive charge is going to be equal to 0. So now what? This F is equal to 0. F will be set to 0. Why? Because affection by both the charges, affections by both the charges, both the parent charges are going to be equal and opposite. So the force on the net force on the testing positive charge simply is going to be equal to 0. So therefore that's 0, which makes that E value. So therefore I can say that E is equal to 0. So now something really important, right, and interesting. We can find a point. Sometimes in these fields, something really important. Sometimes we can find points in these electric fields, right? In electric fields, in such a way that what? Electric field intensity has become the 0. That's the idea. Okay, if I just take that one here, exactly, if I set it there, it's good, right? Fine. So we have found a point in the electric field at which electric field intensity has become 0. Why? Because there is no net force acting on that testing positive charge. Right. Time to define something. If electric field intensity becomes 0, something really important. If the electric field intensity becomes 0 at a point inside a given electric field, such points are known as null points. So we can say it's going to be a null point. Null point. Or sometimes people say neutral points as well. Neutral point. Fine, done. Either a null point or a neutral point. Both things are, both things work. Both the names are okay. Fine. Okay, so therefore electric field intensity became 0. So therefore such a point is called or is known as a null point. So therefore we have just one null point in this particular field line diagram. Right, fine. Having that thing said that way, so we can just go for this point and just say, okay, so this is connected to this one also. Such a point is called null point. So what do you mean by a null point, Mahaputa? A point, very important. What do you mean by a null point or neutral point in an electric field? Is a point at which electric field intensity or electric field strength becomes 0. That's the idea. Got it? Okay. So what do you mean by a null point? A point in an electric field at which electric field intensity or electric field strength becomes 0. That's it. Fine. Okay. Back to the diagram regarding the two negative charges. It's going to be almost same, right? I mean the symmetrical. So I'll take that one here. And let's say the negative charge is going to be somewhere there here. So here we have minus q. Here also we have minus q. Again, let me just place one of these symmetrical line segments to make the reference. It's going to be like that. And probably the first line is going to be the same thing. It's going to be like that. Okay. And the other line segment is going to be like this. And we have the symmetrical lines. The other symmetrical line like this. Probably another one line can go this way, right? So another one line can go this way, and another one line can go that way, and the corresponding line on the left hand side is going to be this way, right? I think in case you will ask, sir, in our diagram, previous diagram, now here, see, that line is pretty straight, but this line is curved like. Most of those points are actually not to be taken into account that much, but actually these lines are going to be little curved at this, I mean in this region, lines are going to be little curved. But once you draw one line segment, this first line as a curved line segment, that's more than enough. So fine. Then after that, we can just keep drawing other lines in the usual way. It's just like that, and I can stay like that, and I can go through this line, and I can draw another line segment here, and another one line segment there, and another one line segment like this. Okay. Well, the diagram is over. Likewise, what about this midpoint, the mid area? It is from here up to somewhere there here. Okay, because we know it's going to be a null point, and from here up to somewhere there, right? It's not going to propagate any further. And then after that, lines. Now this is going to be minus. So therefore, if I place somewhere there here, testing positive, negative, attraction, unlikely, attraction is there. Here also attraction, and attraction is there. Here also attraction. Here also towards the minus q, again attraction. And here also attraction, here also attraction. Okay, having that been said, time to mark the or time to talk about the null points. Of course, yes, there should be a null point somewhere there here on the at the point at which the line segment is q minus q line segment is getting intersected by the perpendicular bisector, in this case in green color. So where they are going to intersect somewhere there here, there should be a null point. Why? If you place the testing positive charge here, the attraction by this minus q. So if you place a testing positive charge here, attraction by this minus q and attraction by this minus q are going to be equal and opposite. They are getting cancelled, so that the what's called this the testing positive charge is not going to move in either way. So somewhere there here we can have a null point. At the same time, this null point or the neutral point is usually represented by the letter capital N is something really important. Is usually represented by the letter capital N. So if I go somewhere there here and just try to make it somewhere there here, somewhere there, and if I just tap like that, it seems better. Okay, why? Because the null point is usually represented by So therefore, in order is one very important statement. It leads to one very important let's say a conclusion. All right, one very important thing to be remembered. If it is just one electric field means electric field is only due to one charge, one particular source charge. There is no chance, anyway, there is no chance for the existence of null points, for the neutral points. Meaning, in order for you to observe or have a null point or a neutral point, at least there should be two electric fields. Because at least there should be two forces for them to get cancelled. We have on that positive, no way of cancelling that force, because it's the only force acting on that testing positive charge. So therefore, in order to obtain null points or the neutral points, at least we need two charges. So therefore, regarding the electric field line patterns or electric field diagrams we drew on the previous day, on the last day, no chance to have what? No opportunity to have what? Null points. Why? Because only one particular charge was there. Only one isolated charge was there. That's the area. Done. Okay. Fine. So therefore, that's going to be a null point again. So if I can just get that one here, and then just okay, this one. Okay. And then like in my handwriting, so I'm going to say it's going to be again a null point. Okay, fine. Okay, right, fine. So that's going to be a null point. This is more than enough. Right. That one is going to be a null point. There. Why? Because forces are getting cancelled. Therefore, that if V is something virtual, but actually it's going to happen in practice as well. Virtually, if we place a testing positive charge, okay, fine. What? There will be two forces. They are equal in magnitude and opposite in direction. Testing positive charge is going to tell me, sir, I feel no net force. Meaning what? There's a point in the electric field. Once after the testing positive charge is placed, that testing positive charge is not acted on by an electric force. Meaning what? There is no electric field at that particular point. Such points are known as null points or neutral points. So therefore, summary, null points are the points at which electric field intensity or electric field strength becomes zero. Right. Now, we were talking about that electric force. The force, right, let's say we have the positive charge here. I just write plus there, and probably we have the let's say another positive charge here. So there will be a repulsive force. There will be a repulsive force, right? That's going to be F. This is also going to be F, and probably this one is going to be plus. That one is going to be minus. So if so, type is going to be attractive. So it's towards each other. Likewise. Right. So now these forces by charges, actually electric charges, forces generated by electric charges, forces generated by electric charges are called Coulomb forces. Coulomb forces. Coulomb means the name of the scientist. Actually, he developed so many mathematical models as well. When it comes to this particular the content or the context, he worked, did some the, let's say, significant. He contributed significantly to develop a theory regarding these electrical forces among electric charges. So therefore, basically, these forces are known as, this force here also is going to be F. Right, here also is going to be F. So generally known as Coulomb force. Coulomb force. Right. Or sometimes we say electrostatic force. Electrostatic force. Right. So this is also going to be a Coulomb force or the electrostatic force. This is also going to be a Coulomb force or the electrostatic force. Very important. One point charge here. Let's say plus Q. It can be plus or minus or whatever. It doesn't matter. Fine. Right. Just let's say magnitude is going to be Q. And there's another charge some distance away. So just to show that line segment, just to show the just for the reference, I'll draw a small line segment there, but this line is nothing, right, other than the reference. So here we have the other charge. That particular line segment is important here. This particular line segment in magenta, or let's say violet, is only for the reference. Nothing like that is existing, is only for the reference. It's a virtual line segment. The straight line which joins one charge to the other. That's all. So let's say this this charge is going to be something like, let's say for example, Q dash. That charge is Q. It can be plus or minus. This is also this is going to be a Q dash. Sign can also be either plus or minus. Now what? In case this is going to be plus, that is going to be minus. Forces are going to be attractive, and they are going to be towards each other. In case this is going to be plus, that is going to be also plus. Forces are going to be repulsive, meaning they are going to act away from each other. In case that is going to be plus, this is going to be minus. Again, forces are going to be attractive. They are going to be towards each other. In case this is going to be minus, that is also going to be minus. Again, forces are going to be repulsive. They are going to act away from each other. That's the idea. So, therefore, one important thing, the signs of these charges, whether Q is plus or minus, and then Q dash is going to be either plus or minus. So these signs associated with this Q and Q dash decides the direction of the force, whether force is going to be towards each other, or away from each other. That's all. Nothing else. Plus plus, minus minus, like charges, they repel. Minus plus, plus minus, unlike charges, they attract. That's all. So minus sign, plus sign, not to be taken into account if it is the case with the forces. Why? Because by using plus and minus, we just decide the direction only, not the magnitude. So therefore, we can just drop the sign associated with the charge in case or just after identifying the directions of the forces. For example, let's say plus Q and minus Q dash. So we're going to decide the forces are attractive, so they should be marked towards each other. That's all. From that point onwards, we can just drop those signs from our memory. Okay, fine. But in some calculations, like in electric potential, the associated sign is very important. So at a point like that, I'll be emphasizing the importance of using the signs or taking the signs into account. Till that point, we have no significance, that much significance about the signs associated with the charges. whether it is plus or minus, minus or plus, what we are going to decide, whether it is going to be attractive or repulsive. That's all. Once that thing is decided, we're going to just neglect the signs. Okay, right, fine. Let's see how it's going to work. Here, now, let's assume they both are positive. Let's assume, because we have to take one case, by somehow one case into account. Let's say, for example, they both are going to be the positive. If so, there will be a force, repulsive force, like that, away from, somewhere there here. And the direction is going to be like that, somewhere there here. And it's going to be like this. That force, let's say, is going to be F. And again, we have the repulsive force on this one also, like that. That repulsive force is going to be away from, like this. This force is going to be F according to Newton's third law. According to Newton's third law, the force by this Q dash on Q is also going to be F. So why? Because action, reaction. Q exerted a force F on Q dash. Therefore, Q dash is going to exert the same force along the opposite direction on Q as well. That is Newton's third law. Right, okay. Now, the separation between two the charges. Let's say I'm going to mark with the same color. And now I'm going to make use of that straight line. Okay. Separation between these two charges, let it to be something like, let's say, simple r. Simple r is the separation. Okay. Now we said the much important work was done by this guy Coulomb regarding these forces. Right. There's something called the Coulomb's Law. The most important the theory in electrostatics. Almost everywhere we talk about electrostatic forces, or just let's say the Coulomb forces. We have to talk about the Coulomb's Law. So why actually this law is this important? Because now these forces, how they are related to the magnitude of the source and the separation between source charges are given, that force is connected to the magnitude of the charges and the separation of the charges by this particular law called Coulomb's Law. Now time to see what is really meant by Coulomb's Law. Right. Before I'm going to go further, I'm going to just write what is meant by Coulomb's Law. Just okay, is Coulomb's Law. Coulomb's Law. Right. What it says is something really important. According to me, Coulomb's Law is not merely something theoretical, meaning it is not like Einstein did, not by thinking. Let's say, for example, Heisenberg did, Maxwell did, Max Planck did. They were known as theoretical physicists. They did everything inside their mind, and they developed mathematical models, and then they came up with some conclusions. Okay, so Coulomb also did so many ample number of experiments and came to a conclusion, actually two conclusions like this. This electrostatic force, so I just by using a different color. Okay, this electrostatic force is related to, number one, the magnitude of this charge. At the same time, magnitude of that charge as well. The connection, that force is also connected to the separation between two charges. This is what he discovered by experiments. So now let's see what he said. This electrostatic force between two point charges, so F, is directly proportional to the product of their charges. Product of their charges, Q into Q dash. Equation number 1, let's say. This is the first conclusion. Second conclusion, this electrostatic force is inversely proportional, meaning 1 over, to the square of the separation between 2 point charges. Separation is R, separation squared is R squared. That is the second conclusion. Both these conclusions were made completely experimentally, meaning these are experimental laws. So what do you mean by Coulomb's law? In just simply by putting them into two statements, electrostatic force between 2 point charges is obvious, right? Electrostatic force between 2 point charges is this one, is directly proportional to the product of their charges. First one. Second conclusion, electrostatic force between 2 point charges is inversely proportional, meaning 1 over, inversely proportional to the square of the separation. So these are the two things, very important thing. Now remember, in case you happen to write the definition of the Coulomb's law, what is meant by Coulomb's law is that the electrostatic, very important, the electrostatic force between 2 point charges, very important, 2 point charges is directly proportional to the product of their charges, Q dash. Charges, and very important, and is inversely proportional, inverse 1 over, inversely proportional to the square, very important. This is not the separation, just not the separation, it's the separation squared, square of the separation between the charges. Okay, so you will be asked to state or just define Coulomb's law. It should be that exactly. Fine. So now time to continue with that, and then I finish it off. So now what I can say is just by using equation number 1, 2, by equation number 1, equation number 2, what we have is F is directly proportional to, like what, Q dash, their product, at the same time 1 over separation squared, or 1 over squared separation. Okay, 1 over separation squared. Okay, so Q dash over simple R squared is there. Now here we have proportionality. I want to convert that thing into an equal sign. So how we can do? F is proportional to, okay, F was proportional to, and now I can just convert that thing into an equal sign by introducing a constant of proportionality, and Q dash, they were there, over simple R squared is there. Okay, well, now that proportionality, these experimental laws, very important, these experimental laws, experimental statements which was given by Coulomb's law, were converted into one equation, and now it is with that form, with one of these constant of proportionalities, right? Then I put on here something really important. Due to historical reasons, there are a lot of things are there to be mentioned. In case I'm going to explain that, because it is the long, and that big background is there, and a lot of things are there to be discussed. In case we are going to we are trying to in case we are going to get into details. So therefore, let me just mention about that thing and go ahead, as because it is not really important at this level. This constant of proportionality, due to historical reasons, very important. So I'm not going to ask you to just Putala, it was from the heaven, not that way. At this, because of the level we are at right now, even though we are not going to even though little capable, we are not going to just bogged into details. How, why, like, right? even though at the end I'm going to mention about I'm going to mention some clues with which you can just visualize, you can just imagine why this thing happened, even due to historical reasons, why this thing happened. Okay, you have some idea with the clues I'm about to the present. So that thing will be done at the end, because those things are not really important. Really important means those things are not compulsory when it comes to exams, but these things are really important. Okay, so let me continue by saying due to historical reasons. Historical reasons. Right. This constant of proportionality K is written as 1 over 4 times pi epsilon. So what? Epsilon. That's called epsilon. It's very important. That symbol is called E P S L I O N, epsilon. So 1 over 4 times pi epsilon. 1 over 4 times pi epsilon. Right. At the same time, I'll mention one more thing. Right. That epsilon is something new to you. You have never discovered, you have never ever discussed about that thing, or never got exposed to such a physical parameter before. Let's say in your O levels, or probably just maybe inside in your school, even though you had done that what's called this electric field stuff at the very beginning. I mean electrostatics, the beginning part. Pretty sure this part has not been done, because what you are learning right now is electrostatic force fields A2 part. Electrostatic force fields, it spreads part of that in A2 and the beginning part in AS. So that is what we have already discussed. E is equal F over Q. At the same time, E is equal V over D. V means the potential difference. D means the separation. Therefore, we can measure that electric field intensity by using Newtons per Coulomb. That's according to the definition. But by using V over D is volts per meter. Likewise. On those things, those theories, basically what we discussed last day was from AS. But what we are discussing right now here, I mean in the second day, is in A2. So you know what? How we are going to just finish this thing off, having completed electric fields entirely, meaning having covered AS part as well as A2 together. It has the continuation. So it is going to, the A2 part is going to strengthen what you absorbed in AS. That's the idea. Okay. So that's what I believe it should be done at the same point. AS as well as A2. In case like one topic is there, splitted into AS as well as A2. I usually, don't believe that thing. Actually that cannot be the best way of learning as well as teaching. So we should be able to complete one topic at one time. Continuously should be able to complete that. Then only you have perfect understanding. Because things can be connected easily only if you do so. And only if the same thing is done by your teachers. Okay, fine. So therefore, K was written as 1 over 4 times pi epsilon. And one important thing, the epsilon is one of the physical parameters which is going to depend on the surroundings of the electric charges. Now, for example, here, if you take this charge and that charge, let's say, for example, these two charges are placed in air, or these two charges are placed in vacuum or free space. These two charges are placed in coconut oil, are placed in water, are placed in kerosene, are placed in wax. Each and every time depending on the medium in which these charges are placed, this particular parameter epsilon is going to change. So can you give one example? Mapata density. You change the density of the medium. For example, let's say water. Okay, I mean you change the water. Oh, let's say water is replaced by coconut oil. Density changes. Why? Density of water and density of coconut oil, two different figures. And you replace that coconut oil by wax, another density. So likewise, you change the medium, very important, medium within which these two charges are placed. Then and then only this particular epsilon is going to change. So on the other hand, so Q dash charges are placed in vacuum. Another two charges are there, Q1, Q2. They are also placed in vacuum. Now what about epsilon regarding these two cases? Mapata same epsilon. Why? Because epsilon is not a fact which is to be decided depending on the charges or the magnitudes of the charges or the signs of the charges. No. Epsilon is something to be decided by the surrounding medium. Meaning, charges are placed in what medium? Is it water? Then epsilon for water. Is it coconut oil? Then epsilon for coconut oil. Is it kerosene? Then epsilon for kerosene. If it wax, then that is epsilon. In that case, epsilon for wax and so forth. Like. So therefore, just tell me one thing. This epsilon is going to change depending on what? Size of the charge, the sign of the charge. No. Only by the surrounding medium. So you need to change epsilon. Yes. You need to change the medium surrounding the electric charges, or the medium or the surroundings of the electric charges. That's the area. Till you do so, epsilon remains constant because it's the constant medium in the surroundings. Done. This particular epsilon, this particular symbol is called permittivity of the medium. That epsilon is called permittivity of the medium. M-I, remember the permittivity of the medium. Right, fine, okay. So that's the epsilon stands for what? For the permittivity. This area. Symbol's name is epsilon. That symbol epsilon stands for the physical quantity permittivity, and permittivity depends on the surrounding medium. Something really important. Surrounding medium. So in a problem, if they haven't mentioned about the particular medium within which charges are placed, you have the total privileges. Complete freedom is there with you to assume charges have been placed in vacuum. Vacuum, another name, free space. Meaning charges have been placed in free space. Right, so as it is the most frequent case, most frequently given medium is the vacuum or the free space. Mabatan, we use a special symbol, special version of epsilon. A special version of epsilon to represent the permittivity of the vacuum or the free space, as it is used so frequently. So I'm going to write permittivity. Probably this is the most frequently used the version in electrostatic problems. Permittivity of the free space or the vacuum or free space is given by, is symbolically represented by epsilon naught. In the data sheet, if you look into this constant K, that constant K value is given. K is equal to 1 over 4 times pi epsilon naught. They have used that, meaning they are going to assume in case one problem will be given from electrostatics, the charges are pre-assumed to be placed inside vacuum unless otherwise stated. That's the idea. So in that case, you can take that permittivity of the free space or the vacuum to be the value they have specified in the data sheet. Usually that epsilon naught is equal to 8.854 into 10 to the power minus 12 farads per meter. Capital F stands for farads per meter. Farad is the unit of capacitance. If you just now get that value, 1 over 4 times pi epsilon K is equal to 1 over 4 times pi epsilon naught, let's say. Now when I write epsilon naught, now Mahaputala can understand, this is the permittivity of the free space, permittivity of the vacuum, meaning charges are supposed to be surrounded by the vacuum, or simply charges are in vacuum or in free space. That's it, right? Fine. So the thing is, if I just the substitute now here, Mahaputame 1 over 4, 1 over pi, they are numbers, ne? So therefore they don't have any units. But epsilon naught does. It is just farads per meter, but that guy is in the denominator. So now that farads per meter should come to the numerator. So per meter becomes meters, just farads becomes per farad. So therefore 1 over 4 times pi epsilon naught units, which is some unit, is going to be meters per farad, / farad is there. Okay, right. So the most important thing here is just this. In case in a problem, you will find out this entire block, 1 over 4 times pi epsilon naught. That entire block simply can be replaced by 9 into 10 to the power 9. So now let's say we are in the middle of a question of finding this electrostatic force or the Coulomb force between 2 point charges. So we're gonna apply F is equal the whatever that K unit is there. Then we know the let's say they have given the values for the charges and the separation as well. So Q value, Q dash value, and simple R value, they all are known to us. And what about here? 1 over 4 times pi epsilon naught. Just Mahaputame replace that 1 over 4 times pi epsilon, the entire block, by 9 into 10 to the power 9. Whether it is given in your data sheet or not given, it is highly recommended. So therefore, once we okay, so we talked about that thing and we got that F is equal to 1 over 4 times pi epsilon naught. That's that entire block was for K. Here we had Q dash over R squared. So one point charge is there, and we have another point charge. So size of that charge is going to be, let's say, probably 2 millicoulomb, simple M, capital C. And we have the other point charge here. That point charge, let's say 3 millicoulomb, and probably say this is going to be minus 2 millicoulomb. That's going to be plus 3 millicoulomb. So I'm not going to write that plus here. There. Now the separation between these two charges, separation between somewhere there, from here to somewhere there. Let's say it's going to be something like probably 9 meters, or probably 9 centimeters. 9 centimeters, right? In case they will ask, find the force between these two charges. Okay, fine. This is going to be minus, that is going to be plus. So the force is going to be attractive, obvious. So let me mark that thing in red. Then you can identify. So it's going to be that way, and this is also going to be this way, and definitely they both are going to have the same magnitude. Why? Because action reaction or action reaction pair. Right, now we go for the theory. I mean, I'll do that part in calculation part in as it was the case here Coulomb's law, blue. Right, so I'm going to say by Coulomb's law, we got that equation, F is equal 1 over 4 times pi epsilon naught, assuming that they are placed in where? Okay, epsilon naught in vacuum. Then q dash over r squared. So therefore, the force F is equal to entire block can be replaced by 9 into 10 to the power 9 multiplied by q, one charge. That's going to be minus 2 millicoulomb. I told you that minusness, plusness, the signs are there just for us to decide the direction. Now directions are decided already, so therefore I'm not going to use that the positive sign or negative sign, because now I'm about to find the magnitude of the force. So only the magnitude. 2 into milli means 10 to the power minus 3. Okay, that's q, into multiplied by then q dash. Q dash is going to be again 3 millicoulomb. Again, milli means 10 to the power minus 3. So that's all, divided by q dash over r. R means 9 centimeters. So 9 centimeters, the entire thing squared. So how it comes? 9 multiplied by 10 to the power minus 2. Why? Because centimeters to be converted into meters. That entire thing squared is there. 9 into 10 to the power minus 2, F is going to be equal 6.67 into 10 to the power 1, 2, 3, 4, 5, 6. 10 to the power 6. Force measured by newtons. So 10 to the power 6 means mega. So if you want, you can just replace that 10 to the power 6 by capital M and N, mega Newton. But my recommendation, leave the answer in 10 to the powers, because usually, I mean, we are not going to go for mega Newtons unless otherwise they wanted you to do so. The only up to about kilonewtons we have in our use. Usually we don't go for the mega Newton. In case you have the mega Newtons or probably giga Newtons or probably tera Newtons, just leave that thing, that tera, giga, the mega part in 10 to the powers. 10 to the power 6, 10 to the power 9, 10 to the power 12 Newtons. That's the best way. Okay, fine. That's going to be the final answer. And why that constant of proportionality takes this odd form, like 1 over 4 times pi epsilon, is beyond actually the scope of the syllabus. Even though I mentioned that's due to historical reasons. Actually, that's due to historical reasons regarding the geometry. Now, time to mention about that thing, because I promised you I'm going to mention about. I'm going to give you some clues. Now, for example, if I ask what would be the let's say volume or the surface area of a sphere. Right, fine. Surface area of a sphere would be what? Surface area capital A would be what? Capital A is equal to surface area of a sphere, right? Not a circle, sphere. 4 times pi. That part is there. Then radius squared. Okay, so this one is going to be a sphere. Then volume of this sphere. Consider again. So again 3 over. Again we have 4 times pi part. If it is something regarding spherical, 4 times pi part is going to be part of the equation, or is going to just contribute. The main reason, now you might ask one question, sir. Okay, fine. It's regarding sphere. 4 times pi comes. 4 times pi comes. 4 times pi comes for each and every equation regarding that. Regarding the properties of that particular sphere. So what is the connection between that what's called this sphere and the what's called this a point charge? So can you guess, Mahmoud? The relationship between that one and let's say, for example, one of these charges, between that point charge and this sphere. Actually, this what's called this point charge. This point charge is obtained by compressing this spherical object, compressing that spherical object equally from all directions. Okay, compress a sphere equally from all directions. You are going to end up with what? With a point. On the other hand, expand one given point along all directions, pull along all possible directions. A point will end up with what? A spherical shape. So therefore, Mapata, point is one of the spheres actually. Point is one of the spheres actually. So we can say not define, but we can mention like this. A point is a sphere of 0 radius. That's the idea. So therefore, I revealed the geometrical, the background behind that historical reason. So therefore, point being the 0 radius sphere, point should also have some kind of spherical parameters. I mean spherical the properties. And that's why regarding these point charges, Mapata, we're going to get that 4 times pi, the portion inside that constant of proportionality. So it becomes a 1 over 4 times pi epsilon, the epsilon, and epsilon was the known as the permittivity. It is one of the very important parameters. Now you got that idea today. You learned that thing today. So just go through that few times today, somewhere there here. That was the tiny problem we did just to verify what you got, just to verify you absorbed that.